Conservation of linear momentum. Before we elaborate this law, conservation law, there are many in physics, it is one of them. But this law is quite universal one, means it is applicable when within the nucleus two nucleons interact or collide, then also it will be applicable, and when two astronomical objects like stars, big giant stars are colliding, then also it's going to take place. Of course, it has one particular condition, that there should be no external force. How will you interpret this law? When there is no external force, the total linear momentum of a system remains conserved. How should the system be? System should be a closed system, means only the internal forces will be applicable or allowed. There should be no external force. For example, there are two objects M1, M2. They are having the speeds U1, U2 before interaction, and finally they acquire the speed V1, V2. You see, when I say interaction, it doesn't mean collision only. Interaction might be coming of two objects closer and then going a little away. This will also be in the category of interaction. So this law is applicable to collision and interaction as well in general. See, momentum initially will be the sum of the two. Only two objects, they are interacting. After the interaction, better to say collision, their momentum would be this much. This is the interpretation of conservation of linear momentum. Here, I haven't used vector on the velocities. Why? Because we have considered it's a 1D motion, it's a linear motion. When the motion is linear, then you need not apply vector over the equations. But if it is a 2D or 3D motion, means velocities are likely to be in second dimension also, in a plane, then in that case you will apply vector. Means vector nature of velocity is very important for this law. Here you can say this whole law is applicable direction wise also, means the collision has taken place. You might say the momentum along horizontal direction will remain conserved before and after collision. Similarly, you might say for vertical direction. So better to say in one sentence that this conservation law is applicable direction wise also. Here, purple color, you see one very remarkable point, it's very important, that this law could be derived from Newton's third law. But this is something which you might deal with reversible angle, that is, from either sides you can proceed. You can proceed from third law and you'll get to conservation of linear momentum. Likewise, you start from conservation of linear momentum and this will lead you to Newton's third law. So either way you can proceed, both are derivable from each other.